Up until now, whenever we've needed data, we would usually just type it right into the file. We would create a JSON file that had various key value pairs, maybe put them inside an array, and then we would read that into our JavaScript. Or perhaps we would serve it as an endpoint on the server that we would access with an AJAX query. So data itself was just hard-coded. It was very ad hoc sort of structured, and the files themselves were static. They couldn't ever grow or change over time. And one could imagine that once you got a few entries in there, say several 100,000, which is not at all unusual, it would get to be a very big file that would be difficult to work with. In order to overcome all this and create something that's a little more scalable and industrial strength, we have what are called databases. And you've no doubt heard of these before. Databases sort of form the general underpinning of just about everything we do with data in computer science, whether you're on the web or working in some other native language. And they come in many flavors, shapes, and sizes. For the web, the most popular way to work with them is to have what's called a relational database, and to get data out of it using something called SQL, or the standard query language, sometimes called SQL. We are going to take a look at the database system that is most commonly used on the web nowadays. It's not the most recent or the most feature-rich, but it is the most traditional. And in fact, it forms the M in LAMP stack, MySQL. To do this, we've got to learn a little bit about how databases work and how they're structured, and the basic idea behind a relational database. So we'll start out looking at that. What are relational databases, and why would you want to use them? Then we'll look at exactly what SQL itself is. SQL will allow us to retrieve data and also rearrange that data into new views as if we're looking at the data from a different perspective. Finally, we'll put all this together and look at how we use it inside of a web environment, namely how we work with PHP, and then also a brief glimpse at where things are headed in the web environment. Hint, it's not relational databases. So to begin with, what exactly are we talking about when we say relational database? The majority of long-used database systems are in fact relational databases. And the idea here is that the context between all the different things that are in the database is maintained as a set of relationships. We know how one object relates to another, and this allows the database to be smart. It can recognize when you're making a mistake. It can keep the tables nice and clean and actually keep data that would otherwise be erroneous from getting into them. Relational databases contain two key components. First, they have entities, or sometimes called objects. And then there are relationships between those entities, hence the name relational database. Those relationships are very important. They establish the connections that are implied by the different objects that you're representing in the database. To get a little more detailed here, let's talk about exactly what these things are. So entities themselves, or objects, they contain attributes, which are essentially the columns of a table. And then they can contain instances, which are the various rows of a table. So an entity itself has several different properties or attributes that go along with it. These are the things that describe the object. And those are usually listed across the top, across the columns. Then as you add objects to the table, you have to have a value for each of those columns, so they go across the row. And each row is a different instance of that entity. The relationships are simply some particular attribute or column in an entity that in fact refers to some other entity in the database, a whole nother table. Exactly how many of those there are and how they refer to one another make the relationships more complex. This all makes a little more sense when we see an example. So let's start out with some data. In this table we have a whole bunch of student data. And if we think about each row in this table as representing a certain entity, well, you can see that that entity is essentially a person, the course they took, and their grade. And that's more or less fits what we have. This is generally how we usually view or deal with raw data. Maybe we throw it in a spreadsheet and it looks like this, where we have different things along the columns and then different values along the rows. But this particular data in its raw form doesn't really acknowledge entities as they exist in the real world. For example, Bart as a person, that's really an entity. And maybe the two properties of that entity would be its name and its email. So Bart's name is Bart, and his email is bart@fox.com. Course could be thought of as its own entity. We have a Computer Science 142, that's one entity. Computer Science 143, that's another entity. Here's that first entity again, so we can start to see here that maybe this is actually a separate entity. And then finally, the grade you've earned in a course could be an entity. It would need to know what course it goes with and what student earned it, but the grade could be an entity all itself. Now this is not a relational representation. This is just sort of a raw data representation. So let's think a little bit about what might be some pros and cons of this particular representation. Initially, we can see it's simple. Everything's all in one place. We look at it. If we go to any particular row in this, everything is there that we need to see. We don't have to go to another table or to somewhere else to get more information. This mirrors traditional tabular data practices, spreadsheets. Everything's all there in one single table. It's all the way we would even write tables down on a sheet of paper. And so there's some familiarity with this approach that can't be discounted. This is also really easy to distribute. If you had a really big table with hundreds of thousands or maybe millions of entries, you could split it up across many servers, and each of those servers can work their task on their portion of the particular table that you're working with. And that's not to be discounted either. In this day and age, as data gets bigger and bigger, being able to split it across multiple servers is a real win. On the other hand, there is a lot of redundant information in this table. Bart and his email is listed twice. Lisa and her email is listed twice. The course name, CS143, is listed twice, as is CS142. And that means that there's a lot of repeated information. Now, don't look at this as a waste of space. It isn't necessarily inefficient in terms of storage. What it is actually one piece of information that's been repeated multiple times. And just like, as I pointed out in the past, when you repeat code, repeating data more than once, when it is in fact only one thing, is an opportunity to create inconsistency. Say, for instance, Bart suddenly changed his name to Danny. We'd have to remember to go change it everywhere it appears in the database. And that makes this difficult to update because it's listed multiple times. Maybe more reasonably, he changed his address to bartman@fox.com. And if he did that, we'd have to change both of these. So redundancy or repeated information creates a chance that something is, or makes something harder to maintain and creates the opportunity that errors will sneak in as the data evolves over time. Searching this is expensive. There are basically no numbers in here anywhere, no easy way to go through and grab something out with simple, quick, and cheap comparison. Now there could be. We could perhaps give each of these rows a number, 0, 1, 2, 3, 4, and so on. But in its raw form, that doesn't exist. Furthermore, creating more complex relationships, like trying to figure out the grade for Bart in Computer Science 142, will absolutely have to be done with strings, because we'll have to find the row where the name is Bart and the course is 142, and then look up the grade. So searching gets to be expensive in a big table like this. Lastly, no single column in this table is unique. Let's sort of see what we mean by that. When we look at name, there are repeated values. So this means that if we were looking at name by itself, it would be ambiguous if we were looking it up by name. Email's the same way because it mirrors name. Courses are the same way. We have 2 for 142, 2 for 143. And then grades, well, because Lisa's a show-off, we have 2 A+. So we have a similar problem here. Grades are not unique either. Nothing in this table uniquely identifies every single row. Now, you can probably guess that that's a problem. Down the road, that's going to create real issues because there's no way, in fact, to ensure that we're getting back the entry we expect. It creates all sorts of problems for searching, sorting, and filtering this data when we go to implement searching, sorting, and filtering algorithms. So, that being the case, this sort of blank raw data approach has been sort of flagged as having issues. It does have some pros. I don't want you to forget those because, in fact, you'll see that nowadays people are moving away from relational databases back to something similar to this. It's really something that's kind of halfway between this and a relational database, but it's still much more similar to this than it is to a relational database. So keep those pros in mind. Those pros are not to be ignored. But the traditional solution to this, the cons were too much, and we had to find a different approach, and that is the relational approach. Here we have pulled out those three exact entities I was mentioning before. So we have one entity called student, and here's the student table. In that table, everybody is listed once. We give them a numerical ID or key, and that is something that's guaranteed to be unique for every row in the table. And then we pull out the information that's relevant only to that entity, which was name and email. Notice this has only 4 entries as opposed to the 6 entries that were in the previous table, so we've saved some space. Course is pulled out as well. We have our 4 courses, and then grades. Grades end up being a combination of a particular student and a course they took in order to assign a grade. The grade is unique according to the combination of both the student and the course. So this in itself, we've got our 3 entities here. They all have unique IDs, this starts to acknowledge the redundant data that was in the prior table and get rid of it. Bring it all back to a central place. Instead of having 2 different columns or 2 different rows that listed Bart, we now just have Bart and his email in one place. And then he's connected to those particular rows through the grade table, where we see his ID shows up as having taken course 1000 or 10,001 and 10,002, and then he earned these grades in those courses. So it's all connected together. These relationships are implied by the keys. So here we have the ID as our primary key. You can see that appearing over here again. And wherever this equals that, that is a relationship. One student here has many grades. One course here, 1000 or 10,001, has many grades. You can see there's 2 grades in here for that course. And if this were a more realistic table with a realistic number of students, courses, and grades, there would be many, lots. This would also get more complex as you start considering multiple sections of a course and courses offered at different terms. And you can just start to see how this sort of grows and balloons in a real-world situation. But here we have a relational breakdown of that same data. Some observations to point out. First of all, we have 3 tables instead of 1, so complexity has gone up. Also, I would argue we have not saved any storage space here. While we did pull out some of the redundancy into individual tables, you can see now we have a table here with 4 entries, a table here with 4 entries, a table here with 6 entries. Back on the previous example, we just had one table with 6 entries. And that kind of balances out. They more or less are equal. Now, as the data grows and there gets to be more and more of it, the relational approach usually wins and does result in less space being used. But it's not a guarantee. And especially when you're using smaller data, like this example, you might actually want to stick with just the plain old table. Of course, we use this example not to say that this is how it would exist in the real world, only so that we can wrap our heads around it. So a real world situation where the data is huge, relational databases are almost always going to win in the amount of storage that they have to use. Here's another example that helps us examine these relations in more detail. This is maybe a little more realistic arrangement of how a particular course might be laid out in a real database. It's sort of centered around the class entity right in the middle. And the class entity is a course name. It also has a section number. It has the number of students registered and the date and time that it meets. On top of that, we have this table here called course, and this is an actual course name and course number. These are connected to class, but class expands it to be an actual offering of the course. So the course has class. I might even call this offering instead. And then the offering has a section number. A professor teaches a particular section of the course. An instructor teaches a class here, so you can notice these are a little bit wonky here. We have both instructor and professor here. Exactly why we have different ones of those, I'm not entirely sure, but it is. Student takes a course. And then finally, a student fills a seat, and seats are part of those courses. Now, I don't really point this out as being like a reasonable way to structure these things. Whoever created this particular database needed this structure for whatever reason. What I want to really illustrate here are the relationships. You'll notice these lines between all of these entities. This is actually what's called an entity relationship diagram. And this particular, or just ER diagram, by the way, and this particular diagram uses a lot of different relationships. Each of the endings on these lines is trying to represent what those relationships are. The most traditional ones are one and many. And you won't find any of those on here because they're using more expanded ones, which are shown below. But imagine here we had one instructor teaches many courses. This would be a one-to-many relationship. And so you would have just one line here, and you'd have the little crow's foot here. This is often called without the line on it. That would be one-to-many. Now, in fact, they're going further. They're saying one and only one. That's what the two lines mean. So exactly one instructor teaches one or more, one or many courses. So this is excluding the idea that there would be zero. So we can't have the instructor be zero. No courses without an instructor, and no instructor is without at least one course. That's what those extra lines mean here. And then you can see how those are explained. One and only one or many. On the other hand, professors themselves, there will be one and only one professor that teaches a section. So no section will be without a professor. However, there may be zero or many courses. So there might be some professors that actually have zero courses they're teaching because of research and things like that. That's not the case at Stout, but at other universities that definitely can wind up being the case. So that's what these additional sort of indicators are. The traditional ones are just one and many. And then whenever you see these extra things like the circle or the two lines or the line on top of the crow's foot, they're just trying to be a little more specific about whether it's exactly one or whether we also allow zero in there. I really don't care. We're not going to have you guys creating these in this class, but you will see me using these. Most of the time I'll always explain what they mean, but it's good to have this as sort of your standard vocabulary because you see these diagrams all over the place. In this class, we will always be using databases that have already been created because this is not a database course. We don't need to learn how to create these things. But it is important that you're able to speak the language and that I can communicate to you what are in these databases. So this sort of a language is how we'll do that, these entity relationship diagrams. Now, let's come back to our particular entity table that we set up. I want to point out a few things about this table that are unique, or rather that are important. As we mentioned before, every table, in order to be a proper relational database, every row needs to be uniquely identifiable. This is done with a primary key. So we have two tables here that have very simple primary keys. The student table includes ID, and ID would be a primary key. So every table has to have a primary key of some sort. Now it might just be a single column, but it might be more complex. But at the very least it must be unique, so that if I give a value for the primary key, I will find one and only one row as the result of that. So this is an essential thing. This is underneath the hood. Relational databases rely on this in order to be able to search and retrieve the data that you are looking for. So both student and course have that. Now the grade table doesn't have that. It has something different. You'll notice here student ID is not unique and course ID is not unique. However, these two combined together would form a primary key. You would never see two instances of 123 and 10,001. That would mean that he took the course twice and earned a grade twice. Whenever you take a course twice, the second grade is the one that counts. It overrides the first one. So you can never have two grades for the same course. So those are guaranteed to be unique. And if it was ever the case that they weren't, that's a sign that something's wrong and we should actually not allow that data into our table. So these two together make up the quote-unquote primary key. And that is allowed. We can do things like that. This particular table is actually just glue between the students and the courses that allows them to come together. And we add the extra grade information just because that is something that's associated with an instance of a student taking a course. Now these two columns right here also happen to be something else. There's something called a foreign key. Foreign keys are ones that are borrowed from another table. And foreign keys always indicate relationships. So if you see a foreign key inside a table like this, that means that there's a relationship between this table and the key that has been borrowed. In this case, we have a case where students are listed multiple times in here. So that means many students can show up in the grade table. So every one student can have many grades. That's what this relationship ends up being, which is what we would have indicated with the connector before. Same thing happens with the course table. Here we have one course shows up many times in the grade table. So this is a one-to-many relationship. Now this is a situation that we've created here where the two foreign keys end up actually creating the primary key for the table. That's not at all unusual. This is actually sort of a many-to-many relationship that we have right here between student and courses. Many students take many courses. Really, the only way to represent that many-to-many relationship is with another one in between that's one-to-many on both sides. And that in-between one fills the glue. This is an instance of taking a course. Bart has taken 1001 and 1000, or 10,001 and 10,002. And so this table indicates that. It also indicates what grade he earned, but that's just sort of meta information that comes along for the ride. The grade table is really the glue between these two. The foreign keys establish the relationship, and the fact that they add up to a primary key, they wouldn't always do that, but most of the time they do. That means it's this sort of many-to-many table that helps a many-to-many relationship actually exist. Now, when these are all established, when you insert foreign keys into another table, you have to tell the database that that's what they are. I would tell the system that student ID is a foreign key from the student table. That means anytime I try and put something into the grade table, as I add the student ID, it's going to make sure that that ID exists in the student table and won't let me add it unless it does. So the database system maintains the consistency when you use foreign keys. This is, as I mentioned before, one of the big benefits of a relational database. All this extra information about how the entities are related allows the database to check itself and to keep itself clean for you. And that's a big bonus. Now, looking at these again, let's think about how we would expand this particular database. If it was just a flat table, we'd just add some more rows. And maybe we need some extra data. Well, we add a column, and we could fill in the old records, or we could leave them empty and just add the extra data in that new row where we need it. So expanding a flat table is something that's generally a little more straightforward. Expanding an existing entity is a little more difficult. Namely, if we want to add attributes to that table, another column, we've got to basically add more data. So when a new column shows up, let's say we want name, email, and now we're going to have address for the students. Why wasn't that there before? Who knows? Somebody goofed. But let's assume we needed to add it. You'd have to go back to every single entry and make sure they have a reasonable value for address. Now, you don't necessarily have to. You could say that address is occasionally empty, but it usually implies some additional work in order to make that happen. Some students will have an address and some won't because the database already existed before we put address in there. It also becomes very difficult to modify the underlying model without corrupting the existing data in the database. My experience has always been this is a little extra work. So you have to watch out for that. Now, keys themselves can be an exception. If you want to add in a key from another table, like a foreign key, then expanding that entry is not as difficult. These keys are usually auto-generated and are just incremented over time in order to make sure that they stay unique. So keys might be an exception here. Expanding the number of tables, say you want to create a whole new entry, that's actually not as difficult. You would simply add a table to the overall structure that's separate from those, and you would expand other tables with the necessary relationships, and so that's where you might be adding foreign keys from another new table. This does still require you to do some work, and there is potential to corrupt it, but the system tends to be more robust to adding new entities than to expanding existing entities. We can actually show an example of this here. Let's say we had student, grade, and course, and now we want to add teacher. So here's the data we have for teachers. We have Miss Crabapple, Miss Hoover, and STEP. STEP is actually the people that made the original textbook that was used in this course a long time ago. They are the ones that are actually the source of this particular set of data. In this case, we add that particular table right here. We don't change grade or student, but we're going to expand the course table so that it includes a teacher ID as well. That indicates which teacher taught it. So now course table has taken on another foreign ID. Now it still has its initial primary key just fine. The teacher ID is not part of that primary key. Maybe it would be if we had multiple sections of the course, but in this simple example we don't. So the teacher ID is just a foreign key. That's all it really is. And so this allows us then to have some more information. And what did we have to change? Well, we created a new entity. That's a fairly harmless thing. And then we expanded course. That's a little more dangerous, but since we're pulling in IDs from over here, it should be fairly straightforward, and most database systems would be able to do that without too much heavy lifting. So keep that in mind. Whenever you've created a particular set of entities, and we call the layout of entities a schema, whenever you've created the schema for your database, if that database has been living for a while and has a lot of data in it and has grown, it can be really hard to modify the schema, to change the number of attributes a table has, or to add additional data into it that wasn't part of the schema before. It's a little bit easier if you're just adding a new entry or a new table into that and need to put some references to that table elsewhere. And this is really what a relational database would want you to do. You'll see in some of our databases, in fact, there's cases where tables got added where they were essentially just attributes that were part of the original entity, but they were forgotten when the entity was created. Because expansion of entities is a little more difficult, it was in fact added as a whole separate table and then just linked back into the original table, even though one could argue it wasn't truly its own entity. We'll talk about that when we see it and point it out so that it makes sense. I really only point this out again so that you understand the limitations of a relational database. The schema resists change, and schemas really have to be completely figured out and set before you can start putting data into the database. The schema being the tables themselves, how they're related, and what attributes they have. Basically, the structure of the table, irrespective of the data. It's sort of the template that the data is going to fit into. That means once there's data in there, changing it, it just becomes hard.